Okay, so covalent lattices, that's what we're going to look at today. From our study design, what we're looking at is understanding structure and bonding of diamond and graphite that explains their properties, including heat and electrical conductivity and hardness, suitability for diverse applications. Investigating the structures, properties and applications of carbon nanomaterials, including graphene and fullerene. So, what we're going to look at is diamond, graphite, graphene, yes they are, and fullerene. So let's take a step back, right? Consider group 4 elements. Carbon is there, it's got 4 unpaired electrons, wants to form 4 bonds, yeah? Compounds may produce small molecules that we're looking at the start of term, or very large ones. So the shape of molecule, Vesper theory around the central atom and so on. So they're small molecules. By definition, molecule means discrete unit. So lattices, there's no definitive end. Now we can produce really, really large molecules. So macromolecules, things like DNA, it's still discrete. It has a definitive number of atoms. Or polymers, it can be thousands and thousands of atoms long. When I look at carbon in particular, these 4 bonds cannot be just to one atom, right? We cannot have a carbon-to-carbon quadruple bond. There's too much strain in that, doesn't exist. It's called dicarbon, yeah. Not any group 4 element, but predominantly we're looking at carbon, right? Other elements, there are some metals that can form more than 4 bonds, but it's not in the context of VCE. So note, I've written there, it's not molecular. Lattice structures are not molecular. There's no discrete unit. So these covalent lattices have different properties. So these are all covalent, right? Covalent lattices. Carbon. Just carbon atoms. All of them have carbon, correct. Lattices are covalently bounded and they're all carbon atoms. It's not molecular. So the definition of molecule is a discrete unit. These are non-discrete, so they're continuous.
So it does have molecules in it?
No, it's got atoms covalently bonded. It's non-molecular, yeah? Correct. Yeah. Lattices aren't molecules. Carbon has what's called allotrope. 3 main allotropes. There's actually, let's say 4. There's another one. So there is graphene. There's also what's called amorphous carbon. So what does morph mean? Change. Right, what does amorph then mean? Not change. So amorphous is carbon without a regular form. So amorphous carbon is soot or charcoal. Right? It doesn't have a regular structure. The 3 main structures we look at: diamond, graphite, graphene, and fullerene.
So they're all allotropes.
Allotropes of carbon. So it's all carbon atoms, but they are structurally different. So I guess it's similar to isotope. Sorry, isomer, right? Isotope is same element, different number of neutrons. Isomer, same molecular formula, different structure. Allotrope, same element, different structural forms. Yeah? Isomer is same molecular formula, different structure. We'll look at isomers later. You may have touched on that last year. So to start with, let's look at diamond. every carbon is bonded to 4 carbon. It's incredibly strong. Right? One of the strongest, hardest substances that we know. It's very strong, it's very hard, it's non-conductive.
But I thought you said that carbons can bond to each other.
They do. They are bonded to one another. And it sublimates. What does that mean? John? Correct. It bypasses the liquid phase. So the amount of energy required to break apart diamond is actually breaking the covalent bonds within it, and it just disrupts into a gas.
Was a diamond, you have diamond gas.
Sort of. It really becomes amorphous. So this is what it looks like. Every carbon is tetrahedrally bonded to 4 other carbons like this. And so on, like any other network. So think about social networks. You've got you connected to your 200 friends, and those 200 friends are connected to their 200 friends, and those 200 friends are connected to their 200 friends, and so on. So we say that Facebook is the largest social network in the world. It's a bigger network than any existing country. If we think India and China with over 1.1 billion people each, right? Facebook, over 2.5 billion members worldwide, interconnected in some way. Some extension, if you're interested, how we might be able to bend diamonds, melt diamonds, or turn your loved ones into a diamond. Graphite. Gonna need a bit of stuff. So graphite is an allotrope, different properties to diamond. Each carbon's only connected to 3 carbons. How many bonds does carbon want? 4. It's only got 3, so what does that mean? No double bonds. 3 single covalent bonds. So what does it mean?
It's not stable.
That's stable enough. Means there's an unpaired electron. So it looks something like this. I want you to imagine this in 3 dimensions. Now, common mistake with this is to do this. Right? This is incorrect. Why is that incorrect? Right, 1 carbon has 4, right? So that's incorrect. So to correct that, looks like this. Right, to represent that. And so this will expand out. Imagine a big sheet like that of hexagonal rings. And they're in layers, so I want you to draw another layer underneath.
Layers.
Yes, not layers. Like onions. Who's seen or is in the musical? I left it too late and couldn't get a ticket. It's all sold out. Anyone seen Shrek? Yeah? The line about how ogres are like onions? They have layers. Right. So graphite is like onions. It has layers. Graphite won't make you cry though. Onions have a compound called a lacrimide that causes your eyes to water. So hexagonal rings, we call this a layer lattice. So diamond is known as a network lattice. Graphite is a layer lattice. Each carbon bonded to 3. Right, it's also very strong. However, it's softer. Still strong, still sublimates. It's softer because it's weak bonds between layers. Dry lubricant means there's no oil, no water present. So, who's got a grey lead pencil? I want you to draw a line on your page. I want you to think about what's happening on the atomic scale with that. Have you drawn the line? What's happening as you draw that line? Have a guess what's happening. As you draw a line with a graphite pencil, what's happening? Well, there's no lead. It's all graphite. It's not a mixture. It's just graphite. So layers of the graphite slide off. There's no lead in pencils. We call them lead, but there's no lead in them. There might be a bit of clay, I don't know. But, so, we've got weak bonds between layers. What type of bond do we expect that to be? What type of bond? Dispersion forces, yeah. Right, so we've got strong covalent bonds within layers, weak dispersion forces between layers. So imagining that in 3 dimensions. Yep. This is inter, yep, so weak dispersion. Strong covalent bonds. So, strong covalent bonds within layers, weak dispersion forces between layers. So what's happening as you draw that line with your pencil is that layers of graphite is sliding over one another and attracting to the page. Ink works differently in that ink is just fed by gravity, goes through the ball rolls onto the page, the cellulose fibres absorb the ink, which is why graphite can be rubbed off and ink cannot. They're essentially an attractive force to the graphite and using friction to rub the graphite layers off the paper. Ink's absorbed into the fibres. Now, the difference with your, who's got the erasable pens? You've got one? Right, the erasable pens have a compound in them that thermally decomposes. So you don't even need the eraser on them. Put them out in the sun, they disappear. Cool. So, graphite is conductive. And it's conductive because every carbon has an unpaired electron. Therefore, it's free moving charged particles and is able to conduct electricity.
So they're all, they're not unstable. How does that say that just makes it so nothing changes?
It is stable, right? Because the layers are so big, the electrons are distributed across the layer.
Sure.
Smaller molecules that have unpaired electrons are unstable and highly reactive. So we can see as an indicator of the strength of the bond is the size of the bond. 14 nanometers, right, is the length of the bond inside a layer. 33 nanometers is the distance between layers. So more than double the size. So the larger the bond length, the weaker the bond. Go through these